Each of us has moments when we gaze up in wonder at the stars scattered across the night sky. It's possible that from somewhere deep in space, someone is admiring a distant shining point, our sun, with similar awe. Perhaps there are countless beings doing the same. What would you say to the 22 trillion potential inhabitants of the cosmos? Such a vast population was once suggested by Scottish clergyman and writer Thomas Dick, who, in 1848, calculated it based on England's population density at the time, 280 people per square mile. Since then, we've explored the planets in our solar system and discovered many distant worlds. But so far, no little green men, alien bugs, or strange creatures have appeared, not a single sign of life. Yet, in a way, Dick might not be entirely wrong. Scientists are now discovering more planets with conditions potentially suitable for life. Let's take a closer look at these worlds on a cosmic journey. A word of caution, this time, be extra careful. You wouldn't want to accidentally step on any aliens. From the past to the present. When did humans first begin to wonder if we were alone in the universe? Perhaps this thought has been around since prehistoric times. But the fascination with alien life gained real momentum in the 17th century when Galileo Galilei used a telescope to explore the heavens. He observed wonders like dark patches on the moon's surface, which he and other astronomers believed were seas, possibly teeming with marine life. Today, we know they were mistaken. Those seas are actually vast plains of basalt formed by ancient volcanic activity. Other thinkers continued to speculate about extraterrestrial life. The philosopher Immanuel Kant even suggested that intelligent beings populated every planet in the solar system, with intelligence increasing the farther a planet was from the sun. His reasoning? Intense solar radiation near the sun would overheat the brains of beings on nearby worlds. So by his logic, Mercury's inhabitants would have little intelligence, while those on Saturn would be veritable geniuses. An imaginative theory, though not exactly scientific. Then there was the renowned astronomer William Herschel, who in the 1870s calculated the height of Martians. Using the most powerful telescope of his era, he estimated Mars's size, its seasons, and the length of its day. He correctly surmised that Mars is smaller than Earth, and thus has weaker gravity. From this, he hypothesized that Martians might be much taller than humans. But as we know now, he never found any actual Martians. Over the years, many other fascinating theories emerged. Yet, despite detailed studies of the Moon and Mars, we have yet to find any definitive signs of extraterrestrial life. Even with the most advanced telescopes and spacecraft, no signs of life have been found within our solar system, causing interest in extraterrestrial life to wane for a while. But recent advancements, like TESS, Kepler, Hubble, and the James Webb Telescope, have renewed hope. These powerful telescopes have expanded the search for habitable worlds, leading to the discovery of over 5,500 exoplanets, including several Earth-like ones orbiting within the habitable zones of their stars. Unsurprisingly, curiosity about alien life has surged once more. Astronomers are eagerly scouring the cosmos for signs of life. While we haven't yet spotted Earth-like animals or traces of advanced civilizations on distant exoplanets, the search continues. One remarkable achievement is the discovery of planets resembling Earth, a shift from earlier finds, which were mostly gas giants. Recently, astronomers identified TOI 715b, a super-Earth 137 light-years away, with a radius 1.55 times that of Earth and a solid surface. This planet orbits close to its star, completing one revolution in just 19 days. If Earth were this close to the Sun, it would be an uninhabitable charred sphere. But TOI 715b survives due to its orbit around a cool red dwarf star that doesn't overwhelm it with heat. However, red dwarfs are known for their volatile flares, which could disrupt or even destroy life on this exoplanet. Yet certain resilient microorganisms might withstand the radiation by hiding beneath the surface, much like extremophiles on Earth. Some microbes thrive in the scalding waters of hydrothermal vents, where temperatures exceed boiling, and Deinococcus radiodurans, a type of bacteria, even survived a year in the vacuum of space, developing cellular repair mechanisms. Such discoveries hint at the possibility of life forms in the cosmos adapted to extreme conditions. Although any detected signals are faint, scientists are actively developing methods to pursue these clues. A recent strategy for searching extraterrestrial life has outlined 4 main principles. The first principle, expectedly, is to identify potentially habitable exoplanets. Scientists will focus on those within the habitable or Goldilocks zone of their stars, where conditions might be just right for life as we know it. Studies from the Austrian Academy of Sciences suggest that planets roughly Earth-sized are ideal. Larger, more massive planets would have intense atmospheric pressure, likely crushing any form of life, while smaller planets can't retain an atmosphere, exposing them to harmful radiation. Without protection, life would be impossible. Many researchers believe a planet also needs a stable atmosphere, tectonic activity, and volcanic processes. Moreover, these conditions must persist for billions of years to give complex life a chance to develop. Though it sounds daunting, a team of U.S. astronomers suggests that planets suitable for life may be more abundant than once thought. They estimate that 1/3 of them might lie within the Goldilocks zone. With 100 billion stars in the Milky Way and roughly the same number of planets, there could be over 30 billion worlds that are potentially habitable. First and foremost, the presence of liquid water is essential for these worlds, as it serves multiple critical roles. Water acts as a solvent for various molecules, aiding in metabolic processes, though it doesn't dissolve everything. It also stabilizes complex organic compounds, allowing them to persist over billions of years, and maintains its unique properties despite external conditions. For a planet to support liquid water, it must lie within the habitable zone where temperatures prevent water from freezing or evaporating. This just right zone depends on the type of star. For yellow dwarfs, like our Sun, it typically ranges from 0.7 to 1.55 astronomical units. However, in the systems of hotter blue stars, this zone lies much farther out, while planets orbiting cooler, dimmer red dwarfs can reside closer in. This concept is a starting point, yet many factors influence a planet's suitability, including its orbital shape. How does an orbit affect the habitable zone? To answer this, international researchers examined over 150 exoplanets orbiting red dwarfs, using data from the Kepler and Gaia telescopes. Their findings showed that circular orbits are more conducive to retaining liquid water, while slightly elliptical, stable orbits help exoplanets rotate on their axes, avoiding extreme temperature fluctuations. As a result, liquid water may be sustainable on some exoplanets, with oceans potentially covering their surfaces. Recently, the James Webb Space Telescope captured a view of K2-18b, an exoplanet located in the constellation Leo, about 120 light-years from Earth, which resides in its star's habitable zone. New data indicates K2-18b may indeed be covered by an ocean, supporting a 2021 study from Cambridge University that identified such water worlds as potentially habitable. However, accurately assessing distant planets presents enormous challenges, especially with variables like temperature. Though scientists can estimate exoplanet temperatures, there is still room for error due to limited data on atmospheres, cloud reflectivity, and the greenhouse effect, all of which influence precise measurements. Misjudging these factors could mean ending up on a scorching or frozen planet instead of a habitable one. Consider Earth as an example. Suppose aliens try to calculate our planet's temperature. They account for Earth's reflectivity, but overlook the greenhouse effect, which could lead them to an incorrect conclusion, seeing Earth as a frozen, uninhabitable world. Similarly, if they only analyzed Venus's cloud cover, they might estimate a surface temperature of -10 solar, despite Venus being incredibly hot. This example illustrates how precise measurements are crucial for assessing the habitability of distant planets. Searching for life beyond Earth may be more productive if we focus on planetary atmospheres. If life exists on these distant worlds, the atmosphere should support its inhabitants, potentially revealing biosignatures, molecules associated with biological processes. The current strategy for finding extraterrestrial life centers on detecting these biomarkers in exoplanet atmospheres. 2 teams of astronomers using the Hubble Space Telescope have already made progress in studying the atmosphere of K2-18b. They found large amounts of hydrogen, helium, and water vapor, suggesting that clouds on this exoplanet could condense and produce rainfall. Additionally, the James Webb Telescope detected dimethyl sulfide, a compound produced primarily by marine organisms on Earth. However, further confirmation is needed to verify its presence on K2-18b. Astrophysicists continue to search other planetary atmospheres for signs of life, particularly for gases like nitrogen, oxygen, carbon dioxide, methane, ammonia, and water vapor. For instance, oxygen might indicate biological activity. However, detecting multiple markers across vast distances is labor-intensive. Recently, researchers proposed a simpler approach. Planets with atmospheres containing less carbon dioxide than their stars may have liquid water on their surfaces, which increases the chances of life. Initial studies confirm that this method is efficient and easier than previous approaches. When comparing Earth to its solar system neighbors, researchers found Earth has significantly less atmospheric carbon dioxide, likely due to its oceans. Phosphine, another promising indicator, could hint at life. For example, phosphine was found in Venus's clouds, which might signal unknown microorganisms, despite Venus's extreme conditions. Data from Japan's Akatsuki spacecraft suggests that Venus's clouds vary and could contain pockets with temperatures and pressures similar to Earth's. Life forms here would be quite different from those on Earth, potentially adapted to high levels of sulfuric acid and minimal water. Life may take on unexpected forms, making it difficult to identify. Planetologist Michael Summers and physicist James Trefil categorize life into three broad types: similar to Earth's, chemically different, and unrecognizable forms that might defy our understanding. This diversity implies that focusing on a broad range of biosignatures, including unusual ones, is essential. To identify life forms that lie beyond our understanding, scientists are exploring a new method: machine learning. AI can analyze spectral data from celestial bodies and detect anomalies, identifying potentially habitable planets even in the absence of known biosignatures. This would ensure that researchers don't overlook exotic signs of life. Yet, theoretical models sometimes clash with real data, highlighting the need for broader exploration beyond atmospheres. Astrophysicists now aim to study exoplanetary surfaces, using advanced telescope observations to penetrate atmospheric veils or dust clouds that obscure these worlds. For example, while we can't directly view K2-18b's surface, atmospheric clues from the James Webb Telescope, such as methane and carbon dioxide without ammonia, support the idea of a vast ocean covering the planet's surface. There are also more imaginative ideas about identifying habitable planets. One suggests that a planet's color might reveal its potential for life. While this might seem odd, let's break it down. During space exploration, if you notice a world bathed in purple hues, it could be more than a visual curiosity. It might signal a habitable environment worth investigating. On Earth, plants are typically green due to chlorophyll, which produces oxygen, a critical element for life. Therefore, we often imagine habitable planets as green. But new research proposes that things might look different on distant planets. Chlorophyll converts visible light into chemical energy, giving plants their green color. However, plants elsewhere might appear purple or violet. In fact, some purple organisms exist on Earth, such as certain algae that harness infrared light. These algae are of great interest to scientists because they thrive in deep ocean regions, converting infrared light rather than using traditional photosynthesis. Although green plants have largely replaced purple algae on Earth, on planets with predominantly infrared radiation, purple organisms might dominate, potentially forming entire forests or fields in rich shades of purple. To explore this possibility, scientists have collected samples from over 20 species of purple algae from a variety of Earth environments, including shallow seas, swamps, and deep thermal springs. Surprisingly, their purple hue results not from a single pigment, but from a combination of pigments, yellow, orange, brown, and red, that together produce the purple or violet appearance. These findings could broaden the search parameters for habitable worlds in the future. Meanwhile, within our solar system, scientists are detecting more biomarkers on planetary surfaces using advanced remote sensing and robotic exploration. For instance, robotic landers and rovers are studying Mars, yielding thrilling results. Methane, a potential biomarker, was detected in the Martian atmosphere, and the Curiosity rover found organic molecules in Gale Crater's rocks. Some of these molecules are stabilized by sulfur, which preserves organic material over time. Although this discovery doesn't confirm microbial life on Mars, it is a promising indication. Essential life-building molecules like DNA and proteins are formed from similar organic compounds, so scientists continue to study Martian organics closely, as they could hint at past life. Some astronomers even believe that these molecules could be fragments of larger, more complex structures, and future missions may dig deeper to uncover them. The Perseverance rover, Curiosity's successor, has yet to find these elusive structures but has made remarkable discoveries. Its most significant finding so far is the detection of organic compounds deep within a rock named Garda. Perseverance drilled into the rock, analyzed the samples, and identified their composition using the Sherlock instrument. Could this discovery indicate life on Mars? While exciting, scientists remain cautious. Organic matter alone doesn't confirm biological processes, as carbon molecules may form through geological activity instead of life. Further research will clarify this, with plans to return samples to Earth for more detailed analysis. Perseverance has already collected 45 sample tubes from Martian rocks and atmosphere, ready for return to Earth on a dedicated mission. The rover continues its work in Jezero Crater, capturing and sending back images and videos, leaving us to wonder what groundbreaking discoveries might come next. The exploration of distant celestial bodies isn't limited to Mars rovers. Space probes have also led to remarkable discoveries, such as those made on the dwarf planet Ceres, the largest object in the asteroid belt between Mars and Jupiter. The Dawn spacecraft, which studied Ceres extensively, revealed its surface to be rich in water ice and complex organic molecules. For years, scientists puzzled over the origin of these life-essential compounds. Were they produced on Ceres itself, or did carbon-rich asteroids deliver them? The presence of these molecules near a 50-kilometer-wide impact crater initially pointed to an asteroid source. However, recent observations have challenged this view. Research from Johns Hopkins University indicates that organic compounds are spread across Ceres, and they remain unusually stable under its environmental conditions, suggesting they may have originated locally. Although Ceres is the smallest dwarf planet in the solar system at just 950 kilometers in diameter, scientists now believe it could potentially support some form of life. What if we expand our search to include planetary moons? Once overlooked, moons have now become prime candidates in the search for habitable worlds, and scientists are increasingly focusing on them. Although no exoplanet moons have been confirmed, potential candidates exist. For instance, the gas giant WASP 12b, located 870 light-years away in the constellation Auriga, might host a moon, as might Kepler 1625b, an exoplanet thought to have a satellite resembling Jupiter's volcanic moon Io. Although knowledge about these distant bodies remains limited, they offer promising new possibilities for exploration. A study from the University of Rochester suggests that a rocky planet with a sizable moon could be especially suitable for life. A large satellite, like Earth's moon, stabilizes a planet's rotation, regulates ocean tides, and contributes to climate stability, factors that can be crucial for sustaining life. Researchers are now focusing on such planetary moon systems in their search for extraterrestrial life. Within our solar system, there are over 200 moons, some with unique properties that make them potential hosts for life. On Saturn's moon Titan, there are both land and seas, as well as 6 elements that are abundant, so scientists believe that there is a high possibility of life on Titan. Let's take a closer look at the possibility of life on Titan. Titan, a moon of Saturn, is huge, second only to Ganymede in size among moons in the solar system. With a radius of about 2,575 kilometers, it is 1.5 times larger than the Moon and about 40% the size of the Earth. Although it can be observed from Earth, it is difficult to observe Titan's interior properly because of its thick atmosphere. Therefore, Titan was a mysterious celestial body shrouded in mystery for a while. However, in 1997, the European Space Agency and NASA launched the Cassini spacecraft to explore Saturn and its moons, and this spacecraft visited Titan. Hundreds of photos and atmospheric composition analysis were sent to Earth, revealing its identity. The image of Titan sent by the Cassini spacecraft was quite ordinary, with mostly wide plains and sand dunes created by the wind in low-lying areas. There were even mountains as high as 3,330 meters. At first glance, these photos looked like hazy days on Earth with dust or fine dust. Clouds were also observed in the sky of Titan. Weather phenomena occurred on Titan similar to those on Earth, with rain falling and lakes forming on the plains, and even seas forming in low-lying areas. Like Earth, liquid circulation also occurs on Titan. With this information, it seems that the speculations of Professor Carl Sagan, who was always right about the possibility of life on Titan, were not true. Or perhaps humans on Earth will one day be able to live on Titan. Because it is located as far as 1.4 billion kilometers away from the Sun, it doesn't receive enough solar heat properly. So as it turns out, the average temperature of Titan is minus 179 degrees Celsius. Titan can be called a supergiant freezer. Normally, if the temperature is minus 179 degrees, all the clothes on this satellite should freeze. Clouds 3 and oceans confirmed through Cassini-5 have a significant discrepancy with what we usually know. The hills on Titan were formed by completely freezing, and the seas on Titan were made up of methane. Also, the clouds were not white clouds gathered by water vapor like Earth, but had a murky appearance. When we only saw Titan in photos, we thought it could be habitable, but it's definitely not a place with a climate like Earth. Even though our environment is like this, scientists' opinions were very positive when Titan was discovered, except for Earth, as it is the only place where liquid is maintained on the surface in a stable way. This is the first celestial body that we confirmed, and there might be life forms here. Also, thanks to the layered structure of Titan, there are winds and rain, making it an optimal place for life. Now let's take a closer look at Titan. Titan has a dense, murky atmosphere. The atmospheric pressure is about 1.45 times that of Earth, and about 98% of the atmosphere is made up of nitrogen with trace amounts of methane. Interestingly, aside from Earth, Titan is the only celestial body in the solar system with nitrogen. Scientists say that Titan's nitrogen-rich atmosphere is very similar to the primitive atmosphere of Earth about 3.8 billion years ago. If we can analyze Titan's atmosphere, we can learn more about the changes in Earth's atmosphere. Currently, nitrogen is the most abundant gas in Earth's atmosphere, accounting for 78%, followed by oxygen at 21% and argon at 0.90%. These atmospheric compositions are present on Earth. However, these ratios have changed slightly over the course of several hundred million to billions of years. Titan's dense nitrogen atmosphere causes a greenhouse effect, which maintains a high temperature despite receiving very little solar radiation. This keeps methane in a liquid and gaseous state. If Titan did not have nitrogen, all of its methane would have frozen, and Titan itself would have become a completely frozen celestial body. Amazingly, the study of Titan has even led to the discovery of some unique molecules that are essential for life formation, such as cyclopropenylidene, which is composed of carbon and 2 hydrogen atoms. This molecule is an important building block for life and also serves as food for other organisms. Although cyclopropenylidene is difficult to pronounce and understand, it is a crucial substance that cannot be overlooked in the formation of life in the universe, and has been observed occasionally in interstellar matter. However, except for Titan, there has been no discovery of such compounds in other celestial bodies, so it's really amazing and remarkable. Cyclopropenylidene, composed of 2 carbon atoms and 2 hydrogen atoms, has been discovered in Titan's atmosphere using the ALMA radio telescope by NASA's research team. The discovery of this molecule, which is difficult to pronounce and has caused quite a stir, is an essential component of the formation of living organisms and can also serve as food for other organisms. Although it has occasionally been observed among interstellar substances in the universe, it has never been found in any other celestial body until now, except for Titan. This is really remarkable, especially considering that it has only been found in 2 places, Titan, which is similar to the primitive Earth environment, and some other celestial body. Moreover, many benzene compounds have also been detected. These compounds play a role in the formation of complex organic matter. In addition, there are other compounds such as argon and carbon monoxide in the atmosphere of Titan, which is conducive to the formation of organic matter during its evolution. It is an environment where organic matter formed during its evolution is falling like light snow. There is one more fact to note about Titan. It is that 82% of its surface is covered with organic matter. According to Dr. Rosalie Lopez, a NASA scientist, more than 82% of Titan's surface is composed of organic matter that has fallen from its atmosphere and has been transported by winds. This means that Titan's organic matter is very abundant, which suggests the possibility of the existence of living organisms. This is an exciting discovery that raises the possibility of the existence of microbial or other life forms. If such life forms were present, there would be abundant sources of food. Another important fact is that there are oceans on Titan. Prior to this, lakes were discovered on Titan, but now it has been revealed that there are oceans as well. If the liquid in these oceans seeps into the subsurface, it could provide sufficient conditions for the birth of life. While this liquid is not water, Titan is the only celestial body in our solar system, besides Earth, where liquid exists on the surface. Scientists have found that Titan's oceans are deeper than previously thought. In fact, during an investigation of one of Titan's seas, Kraken Mare, the equipment that was used to probe the sea was limited by its technological capabilities and was unable to reach the bottom, which is at least 300 meters deep. This is more than 7 times deeper than the average depth of the West Sea, which is approximately 43 meters. In addition, there are geological activities like volcanic activities in Titan, and if such visual activities occur, an ecosystem ranging from microorganisms that use organic matter around the hot springs as food to predators on top of them may have formed. From the beginning, including Titan, organic matter is very abundant, so if miraculously some organisms were discovered on Titan, an ecosystem of organisms and their mothers could have already formed in Titan's seas. The most important clue is this. Recently, it was found that after hydrogen descends from Titan's atmosphere, it disappears from the surface, according to the data collected by Cassini. Some scientists at JPL are claiming that this may be the result of primitive life breathing in and consuming material on the surface. However, Titan's flowing liquid is methane, so if life is actually emerging and surviving here on Titan, the living organisms of Titan may be based on methane. Scientists are looking at Titan's existence of life with a very positive outlook. NASA has started the Dragonfly project to explore the seas of Titan. They will fly a kind of drone powered by a blue-tone fuel to observe various terrains of Titan. The Dragonfly project is expected to launch in 2026 and arrive near Saturn in 2034. They plan to use a parachute to land on Titan when the weather is favorable, and then switch to flight mode to explore and collect samples. Previously, Genius explorations were mostly conducted using ground vehicles, but this method had limitations in mobility, so the goal is to easily explore multiple locations. I will go crazy with my child's drone to explore. The target distance and time for the exploration are about 2 years, 7 months, and approximately 175 kilometers. This distance is twice the distance traveled by all Mars rovers so far. NASA hasn't made a final decision yet, but they say they could send a 1-ton submarine to Titan. The purpose would be to explore the largest Kraken Mare Sea on Titan, which has a fairly deep depth from the beginning. A submarine would be 10 times better than a drone to explore it. If we explore the liquid methane ocean with a submarine, we could thoroughly examine the ocean floor. What do you think about the possibility of life on Titan, Saturn's moon? Imagine a stationary world, ancient, about 4.5 billion years old. It is barely warmed by the sun's rays and covered with a thick layer of ice. This world is smaller than our moon, but slightly larger than Pluto. Its name is Europa, the 6th moon of Jupiter, and one of the largest satellites in the solar system. But what is most interesting about this distant place is that it may harbor life, according to astronomers. Europa is considered one of the most promising places in the solar system to search for new forms of life, all because it has a vast ocean of salty water, ranging in depth from 60 to 160 kilometers. It is hidden beneath a layer of ice with a thickness of 16 to 30 kilometers, but it is still potentially suitable for life. Astronomers claim that water erupts from cracks in the icy crust and is ejected, making it potentially suitable for life. Of course, reaching such a deep environment will not be easy for missions. On the other hand, scientists already have evidence that there are much smaller bodies of water, likely located much closer to the surface of the Moon. They could be situated less than a kilometer beneath the ice. This news brings two positive aspects. Firstly, it increases the chances of life existing on Europa, and secondly, if true, it will make it easier for future missions to search for these life forms. The lead researcher, Riley Kohlberg, accidentally came across a presentation by a colleague who showed a photograph of double ridges on the surface of Europa. Kohlberg remembered seeing similar ridges on Earth, although they are rare on our planet. However, on Europa, they are much more abundant. Subsequent research allowed them to hypothesize that the ridges on Jupiter's moon may be the result of a specific cycle, similar to what occurs on Earth. In this cycle, liquid water freezes and then thaws inside the icy crust, which represents an environment with relatively high pressure. This causes the icy crust to move upwards, creating a two-ridge structure. At least, this is how it happens on Earth. If similar processes exist on Europa, it could indicate the presence of subsurface water. However, the temperature, pressure, and chemical composition on Europa are entirely different, and scientists still don't know how the ice behaves there. Therefore, they cannot understand the depth or size of the water pockets or the time required for freezing. However, it is clear that such a subsurface environment on Europa is likely protected from harsh radiation from Jupiter, which bombards the Moon's surface. This, in turn, increases the chances of life existing in Europa's subsurface. Now we can return to the fact that the ocean on Europa appears to be salty. The red streaks on the Moon's surface may have that color due to their chemical composition. Most likely, they represent a frozen mixture of water and salts. This is quite unusual because this composition does not correspond to any known substance here on Earth. As for the yellow patches on Europa's surface, they may be caused by the presence of sodium chloride. This substance is known to us as salt. Scientists have tried to recreate the conditions on Europa in the laboratory and found that by combining water, table salt, low temperatures, and high pressure, they could obtain a new form of solid crystals. This substance can exist both at the bottom of Europa's ocean and on its surface. However, apart from this information, researchers haven't been able to learn much more. We can only hope that we will find answers to some of these questions around 2030. It is around that time when the Europa Clipper mission, planned by NASA, may reach Europa. The mission plans to conduct several close flybys to determine whether there could be any form of life there in the next couple of years. Europa will be visited by a spacecraft from the European Space Agency. However, Europa is not the only place in the solar system where life may exist or have existed. On our planet, a large portion of this gas in the atmosphere is produced by living organisms, such as methane generated by digestive processes in animals. Scientists believe that methane existed in the Martian atmosphere for about 300 years, but in 2006 it nearly disappeared, about 600 times faster than researchers had anticipated. The question remains, what or who produced this gas, and where did it go? Another Martian mystery involves microbes that may be dormant beneath the surface of Mars. They could have sought refuge from cosmic radiation for millions of years. Scientists simulated conditions on Mars in laboratories to test whether this could be true, and they were amazed to discover that bacteria easily survived in such conditions for 280 million years. This means that if life existed on Mars, we could find evidence of it. Currently, Mars lacks flowing water, and cells or spores would simply dry out. Additionally, the surface temperature is similar to that of dry ice. In other words, the surface is extremely inhospitable. The most likely candidates for life on Mars, if any, are bacteria-like organisms nicknamed Conean due to their rugged nature. Now let's move on to Venus. In 2020, scientists announced that something was found in its toxic atmosphere that could indicate the presence of life. Unfortunately, there was no direct evidence, as there was no opportunity to collect microbial samples or capture images of extraterrestrial life. However, they claimed to have detected a chemical substance called phosphine on Venus, which is highly significant. If this gas is not formed as a result of previously unknown chemical processes, then some microbial life may be involved. Phosphine consists of 3 hydrogen atoms and 1 phosphorus atom. This gas is toxic to any terrestrial life form that requires oxygen, including us humans on our planet. Phosphine can be found in places where there is little or no oxygen, such as swamps and marshes. It is formed as a result of complex mixtures of bacteria living there. It can also be produced industrially. If we think about it, phosphine should not be present in the atmosphere of Venus at all. The formation of this gas requires specific pressure, temperature, and tons of hydrogen. It would not be surprising to find it on Saturn or Jupiter, known gas giants. On this planet, phosphine cannot form naturally, or rather, it may form in small quantities during volcanic eruptions, storms, explosions of minerals on the surface, or when meteorites enter the atmosphere. However, there cannot be as much phosphine as astronomers have calculated, and this should have raised suspicions among scientists. But they were too delighted with their discovery. Perhaps they believe that life may exist on Venus. However, even if this gas was created by some mysterious organisms, it remains a big question how they survived on Venus. On our planet, some microbes can thrive in an environment with only 5% acidity, but not more. However, Venus clouds are composed mostly of acid, with over 90% sulfuric acid. Moreover, the atmosphere of Venus is 50 times drier than the driest place on our home planet. In fact, in 2022, thanks to high-resolution telescopes, it was concluded that there is only a very small amount of phosphine in Venus' atmosphere. So we need to look for signs. Humanity is astonishing with its capabilities and continues to prove that nothing is impossible for it. It is interesting to find out what lies at the bottom of the ocean and beyond the Earth's atmosphere. We create specialized research devices for this purpose. Space on our home planet is limited, but we can create artificial islands. But what can we do if the population reaches a point where Earth becomes overcrowded for all of us? Of course, we can search for planets with optimal conditions for life in other galaxies, and that seems like the most obvious option. But what if we create our own planets in the habitable zone of our solar system? It may sound too fantastic to some, but science has something to say about this. What would such a system with multiple planets look like? How many objects can it accommodate? Can there be more than one planet on a single orbit? And can all the components of such a system revolve around one central object? Before we delve into discussions about our ideal system with multiple planets, let's talk briefly about the current situation with the solar system. While we know about a vast number of planets outside the solar system, currently around 5,000, within the solar system, there are 8 planets. It's worth noting that our system holds the record for the most planets. We know about the TRAPPIST-1 system, which has 7 planets, and the Kepler-90 system, also with 8 planets. These 2 systems share other characteristics as well. The more massive planets are located farther from the main star, while the smaller ones are closer. Additionally, both systems have sun-like main stars. However, there is one important difference in the Kepler-90 system. All the planets are located within 1 astronomical unit from their star, which means they are even closer to their star than Earth is to the Sun. And this is the 3rd planet out of the 8 in total. From this, we conclude that the density in the Kepler-90 system is significantly higher, which means it is possible to create a situation where the distance between planets is smaller than in the solar system. Next, it is important to understand if there is anywhere in the universe a system where there can be more than one planet in the habitable zone. In our planetary system, we have Earth, the only planet with optimal conditions for life during the early stages of the solar system's development. Venus and Mars, which are close to the habitable zone or even within it, could also have been suitable for life. We can take the TRAPPIST-1 system as an example, which contains 3 planets in its habitable zone. Scientists speculate that there may be systems with even 7 planets in the habitable zone. And what about having multiple planets in one orbit? We may not even be limited just 2 planets. There could be more. It is worth noting that 2 Lagrange points, L4 and L5, have a high level of stability in the Sun-Jupiter system. These Lagrange points are occupied by Trojan asteroids, which are located approximately equidistant from the Sun and Jupiter. In theory, not only Trojan asteroids but also Trojan planets could exist, whose positions would practically coincide with these mentioned points. However, such planets have not yet been discovered in the vastness of the universe. We have discussed planets that can form naturally in the universe, but now we will talk about creating systems with the maximum possible number of planets. We can rely on the work of astrophysicist Sean Raymond from the Bordeaux Observatory, who conducted research on this topic. Although his work is not licensed or published in scientific journals, we can extract some relevant information from it. We know that the density of systems similar to the solar system can be an order of magnitude higher. The maximum density value for further discussions will be determined. We will often use the terms sphere or radius in our reasoning. This refers to the space around a celestial body where its gravitational influence dominates. In other words, this space determines the orbits of smaller bodies, despite the influence of a larger object around which the smaller body directly orbits. The Hill sphere is located between the L1 and L2 Lagrange points. For Earth, the value of the Hill sphere reaches 1.5 million kilometers. Since the Moon is about 400,000 kilometers away from its planet, we conclude that Earth's satellite is located within the Hill sphere. The value of the Hill sphere, as we can see, is quite large, and it can accommodate all 8 planets. However, at what distance between planets will the system exhibit stability in terms of interactions between planets? The interaction between planets is strengthened when one enters the Hill sphere of the other, respectively. Destructive processes such as collisions can occur between 2 objects. In the articles by Sean Raymond mentioned earlier, there are studies that state the distance between planets should be equivalent to 5 or 10 Hill spheres. This raises the question of how many planets could potentially fit within the habitable zone of our solar system. It is worth noting that we do not know its exact size. The habitable zone extends from 0.95 to 1.37 astronomical units from the Sun. Taking these calculations into account, Sean Raymond concluded that we could accommodate 6 planets within the habitable zone of our planetary system, where life could potentially exist. So what can we do to increase the number of these planets? It would be ideal to place at least 2 planets on one orbit, with one of them located at either the L4 or L5 Lagrange points. This way, we would have a total of 12 planets, and the system would remain stable. Moving forward, how can we further increase the number of planets based on materials from the journals Celestial Mechanics and Dynamical Astronomy? We conclude that more than 2 planets with equal masses can coexist on a single orbit, provided that the distance between them is at least 12 Hill radii. The minimum number of planets on one orbit would be 7, similar to Earth's orbit. Under such conditions, we could have as many as 42 planets. As we recall, there can be 6 orbits within the habitable zone of the solar system. Could there be such a number of planets on each orbit? The mass of the planets does not significantly affect the distance between orbits. Therefore, if we place 42 planets on 6 orbits, we would have a total of 252 planets with optimal conditions for life. The spacing between orbits largely depends on the influence of one planet, specifically the planet that another planet from a different orbit comes under the influence of. Let's go even further and try to increase the number of planets. Here we need retrograde orbits. In the solar system, planets move along their orbits in one direction. If the distance between planets is relatively small, the planets on different orbits, including gravitationally, influence each other, leading to instability. If 2 planets stay close to each other for an extended period, the consequences can be serious. In such cases, it is better to isolate these 2 planets from each other so they spend less time in close proximity. How can we achieve this? We need these two bodies to move in their orbits in opposite directions, resulting in retrograde motion. By doing so, we not only reduce the gravitational influence of some planets on others, but also decrease the distance between the orbits. If we raise the stakes, so to speak, we might be able to form habitable planets outside the habitable zone. Our limit would be 1,000 astronomical units, based on the works of Sean Raymond. This is the optimal distance from the main star, as the external influence on planets will not be significant. Thus, within this zone, we can place 57 rings, each containing 42 habitable planets, resulting in a total of 294 objects. Even though such a quantity may seem incredible and extraordinary, it will not outweigh the total mass of the main star. The Sun will still be orders of magnitude more massive than all the objects in the system combined. Indeed, our reasoning is currently fantastic and purely theoretical. Of course, something like this cannot form in our solar system. However, over time, we may discover planetary systems similar to the ones we described. What do you think? Do you expect such discoveries in the future? And if so, how soon? Just imagine an endless plain, and there's a descent covered by waves of an eternally restless sea. To all this, add extreme pressure levels and immensely powerful winds. The sky is completely covered by a dense blanket of clouds, and only in the distance does a red sun peek out on the horizon, just for a moment, before hiding behind the clouds. Now, you can barely see it. The sun doesn't actually change its position, but that didn't stop it from disappearing from our view. Look around. It seems like the last place where any living organism could exist. However, it's not that simple and straightforward. We have just described to you how the so-called second Earth on this planet could look like. Researchers may also start searching for extraterrestrial life forms. So what kind of astonishing planet is this? We're sure that after watching our videos, you might have had the desire to work in the field of space exploration. However, remember that there's plenty of work to be done on Earth as well. As you know, in the last decade, scientists have discovered a huge number of exoplanets. Currently, there are 4,370 of these objects, located in approximately 3,230 planetary systems. Among them, around 3,000 planets are in the confirmation stage of being exoplanets. Typically, these objects are of enormous size, including gas giants, super-Earths, and super-Jupiters. Technical exoplanets are large bodies that orbit their stars in a relatively short period of time, making them much easier to detect than smaller planets. Exoplanets can amaze us not only with their sizes, but also with the possibility of hosting living organisms. The number of candidates in this regard is in the dozens, and they become a piece of home for researchers. Among such exoplanets, GJ832c stands out. It is located in the constellation of Grus, and scientists believe that it has the highest probability of hosting life among all known exoplanets. The main star around which this object orbits is named Gliese 832. The distance between it and our Sun is approximately 16 light-years. Gliese 832 is a relatively dim, red-colored object with a luminosity of about 0.7% of the Sun's luminosity. The mass and diameter of the star are approximately 50% of the Sun's respective values. The temperature on Gliese 832 is around 326 degrees Celsius. Due to this, the habitable zone around the star is quite narrow. Objects within this zone will experience tidal locking, meaning they will always have one side facing the star. The most famous example of tidal locking is the Moon and Earth. It is known that there are two planets in the habitable zone of Gliese 8832. One of them is Gliese 832b, discovered in 2008, which has characteristics similar to Jupiter. Its mass is about 2/3 of Jupiter's mass. The distance between Gliese 832b and its star is approximately 3.4 astronomical units. In 2015, a second planet, Gliese 832c, with an Earth similarity index of 0.81, was discovered. This is considered a high value and didn't go unnoticed by the global scientific community and, of course, sensation-seeking journalists. As a result, Gliese 832c acquired another name, Second Earth. However, Despite these two planets sharing similarities, there are many differences between them. Nevertheless, the Earth Similarity Index of Gliese 832c is very high, and its mass is equivalent to 5.5 times that of Earth. The orbital period around the main star, Gliese 832c, is 35 Earth days. The distance between the star and the exoplanet is 0.16 astronomical units. It's worth noting that the distance from Earth to the Sun is defined as 1 astronomical unit. One peculiar feature of Gliese 832c is that due to its relatively wide orbit, it may occasionally leave the habitable zone. As a result, rapid temperature fluctuations are characteristic of this exoplanet. The amount of energy that Gliese 832 provides to the exoplanet is essentially equivalent to the amount of solar energy that Earth receives. The temperature on the planet itself reaches -20 degrees Celsius. It is assumed that the atmosphere of Gliese 832c has a relatively high density, which can increase temperature levels. We have already mentioned the high probability of the exoplanet being in tidal locking with its star. Additionally, its habitable zone is relatively narrow, indicating a small distance between Gliese 832c and its star. Since exoplanets are always tidally locked to their main star, there are significant temperature variations between the illuminated and unilluminated sides. If the atmosphere's density is sufficiently high, storms can occur on Gliese 832c. In the Gliese 832 system, there may actually be not 2 but 3 planets. Scientists from the University of Texas at Arlington concluded this in 2017. The estimated size of the presumed third planet is approximately 10 to 15 times the mass of Earth. It is located at a distance of 0.25 to 2 astronomical units from its main star. The existence of the third planet has not been confirmed yet, as more data is needed. However, let's return to Gliese 832c. Let's imagine how this exoplanet would look if it had living organisms. The gravity level on Gliese 832c should be noticeably higher than on our planet. We don't know the exact diameter of the planet, so we cannot determine its gravity precisely. However, we do know that the density of Gliese 832c is similar to that of Earth, so its gravity could be approximately 3 times that of Earth. These measurements would contribute to the formation of a more even relief and the depth of oceans on Gliese 832c. These conditions can be considered favorable for the emergence of living organisms, as there will be more areas where potentially warm water can exist. Regarding the appearance of Gliese 832c, the most likely scenario is that the relief formations will be of a reddish color. This is due to the dim light and high atmospheric density. Because the exoplanet is in tidal locking, the unilluminated side will have high temperatures, while the illuminated side will have lower temperatures. There will be a ring-like region where the illuminated side transitions to the unilluminated side, and this area will have the most favorable temperature for the development of living organisms. Precipitation in the form of liquid water will be abundant at the boundary with the dark side, where glaciers would melt. As a result, the amount of water would increase. However, a significant drawback in this case would be the incredibly strong winds caused by temperature differences. These winds could be restrained by high mountain formations. However, due to the gravitational forces, these mountains would not be of sufficient height for that purpose. The exoplanet moves in an elongated orbit, but it is relatively small due to its close proximity to its main star. As a result, the change of seasons occurs approximately once a week when the exoplanet is closest to or farthest from its star. When it is closest, summer arrives, and when it is farthest, winter comes. The inclination of the planet will not play a significant role. It is the distance between Gliese 832c and its star that determines the seasons. It is presumed that in the ring-like region of the exoplanet, the change of seasons will have a similar effect as tidal forces on Earth, causing tides and periodic flooding of certain areas, followed by water receding. During these processes, particles of different substances enter the water, creating an ideal environment for the development of living organisms. Scientists suggest that life on Gliese 832c may thrive exclusively in a watery environment. The effects of gravity and temperature variations in the ocean are significantly reduced. potential living organisms could adapt to frequent changes of seasons by migrating to more comfortable areas or entering a state of dormancy, making harsh conditions less of a concern for them. Now let's imagine how these living organisms, if they ever appear on Glacier 832c or have already started to appear, would look like. Plants, most likely, would resemble mosses and have a dark color to maximize their solar energy absorption. To withstand strong winds, they would need sturdy roots. Due to the high atmospheric density, there could be atypical forms of organisms that develop directly in the atmosphere rather than on the surface. They would move with the direction of the wind and extract necessary substances from the air for their vital processes.